Welcome to our world, driven by electrical power. It's hard to find any part of our lives which does not benefit from electrical technology. It is everywhere. It's easy to take it for granted, but this electrical world is constantly in motion. It is the collective work of millions. Engineering and understanding the materials used in our electrical world is the keystone to making it all run. Advancements in materials directly leads to advancements in technology. Smaller, faster, more durable, flexible, more precise. All of these are the results of improvements in materials and design. So what are the materials that make it all work? And how do we get these materials from nature? Copper. For 10,000 years, copper has accompanied humankind on its technological journey. In the last 200 years, copper re-emerged as the most important non-structural metal, and that was due to its electrical properties.
In modern times, we use copper in many different applications, and it's because copper has a lot of really unique properties.
It's the really good connectivity that it has that allows you to be able to use it for all these electrical things.
Well, copper globally is an indispensable metal and almost a benchmark for the advancement of world economies and development, if you will.
So where do we use copper and why?
So here we have 4 everyday items that you probably recognize. They all contain copper. Now copper has 4 major uses in our electrical world, and in order to take a look at those 4 uses, we're going to have to take a look inside. Here we have a circuit board, and on the circuit board are integrated circuits. Integrated circuits are considered the brains of modern technology. Copper is also used in wireless technology to send and receive messages ranging from your personal phone calls to national defense. This is copper wire. Copper wire is used as a pathway to transmit power into your home, school, or business, but it can also be used on a microscopic scale in electronics. This is a transformer. A transformer contains an electromagnet, which is the 4th use of copper. Electromagnets are used to generate power, transform power, or convert power back into motion. So it's great that we know all this, but that's not the whole story. So how does copper go from this to this? Let's find out.
Copper is one of many elements present in the Earth's crust, and a typical deposit in copper is called a porphyry.
Porphyry is a geologic term that's used to describe intrusive igneous rocks. The magma chambers or reservoirs are very complex and dynamic systems. In addition to having magma, they also have associated with them hydrothermal or hot fluids, as well as steam. The steam and the magmatic or hydrothermal fluids carry metals.
And then over time, when there's exposure of the sulfide mineralization to the elements, weather, heat, oxygen from the air, you get a weathering process of the sulfide mineralization. And the sulfides oxidize and become sulfuric acid and drain down in the deposit. They carry with these liquids, they will carry copper mineralization. Copper comes in 3 basic forms: copper sulfides, copper oxides, and native copper. Native copper is rare, so in mining we're mostly dealing with sulfides and oxides. In copper processing, typically there are 2 modes for creating copper metal. In hydrometallurgy, we recover copper by use of water-based chemistry. In pyrometallurgy, we recover copper by means of heat. A rock is a composite of a lot of minerals. say chalcopyrite or bornite. Malachite and cuprite may also be the copper ore contained in the rock. The rest of the rock that does not contain copper ore is called gangue. At Morenci, yes, they engage in hydrometallurgical processing. They also do crushing, grinding, flotation of sulfide minerals to make copper concentrates. Hydrometallurgy is mostly used on copper oxides because they are easily solubilized in acids. Copper ore is then wetted with dilute sulfuric acid in an agglomerator just before being heaped. Then they'll use a process of heap leaching, where weak sulfuric acid is sprinkled on the material and the copper oxide is released. The dissolved copper is recovered in a lined impermeable pond and sent to solvent extraction, or SX. And then it's concentrated and purified with solvent extraction. That's the primary process hydrometallurgically for the last 40 years. And then the copper metal solutions are reduced using what we call electrowinning, where we use electrical energy to reduce the copper to copper metal. That started first late in the late 1960s, early 70s at a place called Rancher's Bluebird in the United States, so it's a recent event. When 100-pound sheets of electro-1 copper are popped off of the cathode and stacked into bundles. The cathode bundles are then loaded into rail cars and shipped to factories for transformation into final copper products. Copper sulfides require pyrometallurgical smelting since they are not as readily soluble as copper oxides. So we go through crushing and grinding, crushing in a sag mill and grinding in a ball mill in order to liberate the copper minerals away from the waste minerals or the gangue, so they're no longer connected. And then the sulfide minerals are selectively concentrated by a process called froth flotation. Where we add chemicals to a water system. And what happens is materials within the Earth's crust, sulfides or the like, are either hydrophilic or hydrophobic. That is, they're water-loving, hydrophilic, or water-repelling or hating, hydrophobic. So by adding what we call collectors, like xanthates or dithionophosphates, you can get a monolayer coating on the sulfide mineral that will make it hydrophobic and correspondingly aerophilic, so it likes air. So as we change the surface chemistry of the particle, it will be repelled by water and attach to an air bubble that you put in the solution. There are several stages of froth flotation. At each stage, the solids become more purified. After flotation concentrates the copper ore, the water must be removed. This is done in a tank called a thickener. The thickened solids are then filtered. At the end of filtration, the copper concentrates have about an 8% water content. The filtered copper concentrate is then piled and loaded onto train cars. These are then shipped to a smelter where so-called pyrometallurgical techniques, that is, no water and a lot of heat, are used to smelt them, converting and then finally refining to form copper metal. And that's a very ancient and historic method of copper production.
So why is copper so special? What about copper as an advantage over aluminum, steel, or silver? Firstly, we look at cost. What is really practical and affordable for widespread use? Next, we look at what materials have a good conductivity. And finally, we look at durability, melting point, flexibility, and electrical conductivity. Copper is able to bend without being very brittle. So copper is excellent for wires because of this property. Another great property of copper is its electrical and thermal conductivity. These are related, and this is because of its atomic structure.
Atomic number of copper is 29. That means it has 29 electrons, and when the copper metallic bonds are formed, the last two electrons are more free, so they can move around the lattice much more easily. So copper in the metallic bonds has so many extra free electrons to move around, so that's why it's a good conductor of electricity.
Copper, believe it or not, is made of crystals. Not these crystals, but tiny microscopic crystals. The longer the molten metal takes to cool, the larger the crystal. In metallurgy, we call crystals grains. In each grain, copper atoms are lined up in a lattice. If you were designing an electrical product, you might want your copper to have different properties. By changing the impurities, like the oxygen content or alloy, you can change the performance. The way you work with metals can also give you desired results. By cold working your metal, you create many dislocations in the grain structure. With a tangled set of dislocations, it becomes stronger. So what are the four major uses of copper? In order to transport electrical energy, we use a wire. Wires come in all forms, from thick braided lines to microscopic paths and devices. Copper has a number of advantages that make it good for wires, including the ability to carry more current in a smaller cross-section.
About 60% of what's mined today is used in electrical wiring, both commercial wiring as well as residential. And then about 20% goes into plumbing as well as roofing, and 15% goes into the manufacture of industrial machinery, and then the remaining 5% is used in alloys, primarily brass and bronze.
Right from the beginning of the power grid, copper is important in the form of an electromagnet. The electromagnet is most often found in the shape of a solenoid. The solenoid is formed by a coil of insulated copper wire energized by electricity. Copper has such a good conductivity that a solenoid made of it can be more compact and can handle higher current loads. Electromagnets are used in generators, transformers, electric motors, lamps, and lots of other things.
Any motor or generator is basically two magnets. You have one magnet in the stationary part, and the other magnet in the rotating part. If you push it the way it doesn't want to go, you put in mechanical power and it comes out electricity. You let it go the way it wants to go, you put electricity in, it comes out mechanical power. But it's the interaction between two magnets that converts the mechanical to the electrical, or electrical back into mechanical.
Generators depend on two solenoids passing by one another. This cuts the magnetic lines of flux and converts movement into energy. Copper is vital for our wireless world. Copper is the most efficient material for high-powered radio transmission. Copper is an important material in major telecommunication systems. It is important even on a small scale in every home. How would our world look without mechanized brain power? Integrated circuits and electric components have depended on copper since the beginning of the electrical age. As we have moved from large components to small chips, the trick of making ICs was developed.
So the integrated circuits are made using a silicon wafer like this. They start with a silicon wafer like this and then start making the transistors and resistors and capacitor component in this wafer. But these days, people figure out how to deposit copper, how to remove copper, and also by using some special material like tantalum nitride, people could prevent copper moving all over the place. So copper is much more common nowadays in very high density integrated circuits.
The four major electrical applications of copper touch every part of our lives. New high-efficient motors and green technology depend even more on copper. It would be hard to imagine our world today without it. While silver and aluminum can act as good conductors, copper is by far the most prolific material for electrical purposes. And if we learn about how it got here, from mountain to fine particles, to slurry, to cathode, to wire, and then to the device, we really begin to appreciate things. With materials engineering and metallurgy, we continue to stretch what we can do with copper. Let's see what the future brings.